Hello everyone, welcome back to the video lectures on digital signal processing, and we are studying discrete Fourier transform and its properties, and this is lecture 5. We were solving problems, so let us continue solving the problems. Explain how to find the IDFT using DFT. So using DFT we have to find out the IDFT formula, or in other words, from DFT we find the IDFT. Let us take the formula of IDFT. So we have x of n equal to 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of minus nk. Let us apply conjugate on both the sides. So conjugate of x of n is equal to 1 by n summation k equal to 0 to n minus 1. So when you have to apply conjugate, and this conjugate I'll bring inside, so I'll get 1 by n summation k equal to 0 to n minus 1 conjugate of x of k, and conjugate of wn to the power of minus nk will be wn to the power of nk, because wn to the power of minus nk is e to the power of minus j 2 pi by n into minus nk, so minus of minus it will become plus, and this is cos 2 pi nk by n plus j sin 2 pi nk by n. Now if I take the conjugate, that will be cos 2 pi nk by n minus j sin 2 pi nk by n, and that is nothing but wn to the power of nk. So after taking the conjugate, so conjugate of x of n is equal to 1 by n into, this is equivalent to the DFT formula, where we write instead of n we have k here. So original DFT formula is summation n is equal to 0 to n minus 1 x of n wn to the power of nk. So in this form here, instead of n k has been written, and instead of k n has been written. So summation k equal to 0 to n minus 1 conjugate of x of k wn to the power of nk. So k is written instead of n, and so k is written instead of n, and n is written instead of k. So this is equivalent to DFT of conjugate of x of k, or x of n is equal to, I find the conjugate, so I'll get 1 by n into DFT of conjugate of x of k whole conjugate. So this is the formula to find IDFT using DFT. Now in the question, find the IDFT of the 4-point sequence using DFT. X of k is given. You have to find out IDFT using DFT. So the formula we had just now derived was x of n is equal to 1 by n DFT of conjugate of x of k whole conjugate. Now x of k is given, we want conjugate of x of k. So conjugate of x of k is 4 minus j2 conjugate will be plus j2, then 0. For j2 it is minus j2. And now we have to find out DFT of conjugate of x of k. So DFT of conjugate of x of k will be summation k equal to 0 to n minus 1 conjugate of x of k wn to the power of nk. So anyway, conjugate of x of k is the series here, and when we expand the series, n is equal to 4, so n minus 1 is equal to 3. So this is equal to summation k is equal to 0 to 3 conjugate of x of k w4 to the power of nk. So that when we expand, we get substitute k equal to 0, then substitute k is equal to 1, k equal to 2, and k equal to 3. So this will be equal to conjugate of x of 0 is 4, conjugate of x of 1 is j2, and then w4 to the power of n. Conjugate of x of 2 is 0, then conjugate of x of 3 is minus j2, w4 to the power of, sorry, here n I have forgotten, so 3n. So what are the terms you are going to get? Substitute n is equal to 0, then the value will be 4 plus j2 minus j2, that will be 4. Next, substitute n is equal to 1, then this value will be 4 plus j2 w4 to the power of 1 minus j2 w4 to the power of 3. And we know w4 to the power of 0 is 1, w4 to the power of 1 is minus j, w4 to the power of 2 is minus 1, w4 to the power of 3 is plus j. So this will be 4, w4 to the power of 1 is minus j, so j into j is minus minus plus, you will get plus 2. w4 to the power of 3 is j, so j into j minus 1 minus minus plus, so you will get 8. Next, substitute n is equal to 2, so we will get 4 plus j2 w4 to the power of 2 minus j2 w4 to the power of 6. w4 to the power of 2 is minus 1, w4 to the power of 6 is equal to w4 to the power of 2, so minus 1. So you have 4 minus j2, and this will become plus j2 4. Next, substitute n equal to 3, w4 to the power of 3 minus j2 w4 to the power of 9. So for w4 to the power of 3 is j, so j into j we have minus 2. w4 to the power of 9 is nothing but w4 to the power of 8 plus 1. That is w4 to the power of 1 is minus j into minus j. So it is minus 2. So answer is 0. Now from the formula, x of n is equal to 1 by n. So in this case 1 by 4. And whatever DFT result we have got, conjugate of that. DFT result is 4840. All are real numbers. So this is equal to divide by 4. So we will get 1, 2 1 0. So x of n is 1 2 1 0. Next question, let xp of n be a periodic sequence with the fundamental period n. If the endpoint DFT of xp of n is equal to x1 of k, 3 endpoint DFT of xp of n is x3 of k, find the relationship between x1 of k and x3 of k. Verify the above result for the sequence 2 1 and sequence 2 1 2 1 2 1. So what is given is endpoint DFT of xp of n is x1 of k and xp of n is periodic sequence. So when xp of n is periodic sequence, what does it mean? Xp of n equal to xp of n plus n equal to xp of n plus 2n, etc. That is the first statement. Second statement is endpoint DFT of xp of n is x1 of k. Endpoint DFT means, what do you say? x1 of k is equal to summation n is equal to 0 to n minus 1 x1 of n w n to the power of nk. Then that is, it is x1 of k is endpoint DFT of x1 of n. From x1 of n you apply endpoint DFT, you get x1 of k. Similarly, x3 of k is 3 endpoint DFT of xp of n. So xp of n we have to take. So xp of n, apply 3 endpoint DFT, you get x3 of k. That means x3 of k equal to summation n is equal to 0 to, it is 3 endpoint DFT. So 3n minus 1 xp of n w 3n to the power of nk. So this we have to now find out the relation between x3 of k and x1 of k. So this summation n is equal to 0 to 3n minus 1, will split it so that each summation contains n points. So we write 0 to n minus 1 xp of n w 3n to the power of nk. Next, summation n is equal to n to 2n minus 1 xp of n w 3n to the power of nk plus summation 2n to 3n minus 1 xp of n w 3n to the power of nk. Now this is equal to summation 0 to n minus 1 xp of n w 3n to the power of nk plus, now if this summation, these limits I want to change to 0 to n minus 1, that means I'll be subtracting n from the limits. So I should add n, or in other words replace n with n plus n. So summation n equal to 0 to n minus 1 xp of n plus n. So wherever n is there, I am writing n plus n w 3n to the power of n plus n into k plus summation, here this is 2n to 3n minus 1. So we'll subtract 2n from the limits and add 2n wherever n is there inside. So n is equal to 0 to n minus 1 because I have subtracted 2n, and here I have to add 2n. 3n n plus 2n into k. Now because xp of n is periodic, so summation n is equal to 0 to n minus 1 xp of n w 3n to the power of nk plus summation 0 to n minus 1 xp of n plus n is equal to xp of n, and this we will split, we will get w3n to the power of nk into w3n to the power of capital Nk plus summation n is equal to 0 to n minus 1. Once again, xp of n plus 2n is equal to xp of n, and this we will split w3n to the power of nk, w3n to the power of 2nk. So here w3n to the power of nk can be written as wn to the power of nk by 3, because e to the power of minus j 2 pi by n 3n into nk can be written as e to the power of minus j 2 pi by n, and this 3 I can take and write it as n into k by 3 like this. So this is wn to the power of nk by 3. Similarly, w3n to the power of capital Nk is equal to e to the power of minus j 2 pi by 3n into nk. So k cancels. So this will be equivalent to w3 to the power of k. E to the power of minus j 2 pi by 3 is w3 to the power of k. So similarly, w3n to the power of 2nk will be w3 to the power of 2k. And we can take out this summation common. Summation n is equal to 0 to n minus 1 xp of n w, wherever 3n to the power of nk is there, I'll be replacing it with wn to the power of n k by 3, and when I take this common, I'll get here 1 plus w3n to the power of nk, I'm writing it as w3 to the power of k, and next w3 to the power of 2k. Now if I compare this summation with the summation of which gives us x1 of k, everything is same except here k is there, here k by 3 is there. So this summation xp of n wn to the power of n k by 3 is equal to x1 of k by 3. So instead of k, because k by 3 is there, instead of x1 of k, we will write x1 of k by 3, and into 1 plus w3 to the power of k plus w3 to the power of 2k. So this is the relationship between x3 of k and x1 of k. Now the second part of it is verify the above result for the sequence 2 1 and 2 1 2 1 2 1. So we have x of n as 2 1. Two samples are there to so find out 2-point DFT, because n is equal to 2. So this will be summation n is equal to 0 to n minus 1. So 1 x of n wn to the power of nk. So that will be equal to, you substitute n is equal to 0 and n is equal to 1. So 2 plus w2 to the power of k. Now 3n will be 6, and the sequence is 2 1 2 1 2 1. I'll write this as x1, this as x2. That is, it is just repetition because we are taking n 3n. So x3 of k is equal to summation n equal to 0 to 3n minus 1, that is 6 minus 1, 5 x of n w6 to the power of nk. So this will be 2 plus w6 to the power of k plus 2w6 to the power of 2k plus w6 to the power of 3k, 2w6 to the power of 4k plus w6 to the power of 5k. So here 2 plus w6 to the power of k plus, here from these two I will take w6 to the power of 2k common, so I'll get 2 plus w6 to the power of k. Similarly, from these two I'll take w6 to the power of 4k common, so I'll get 2 plus w6 to the power of k. So in all these cases 2 plus w6 to the power of k I'll take common, and we will get 1 plus w6 to the power of 2k plus w6 to the power of 4k. Now w6 to the power of k is e to the power of minus j 2 pi by 6 into k. We can write this as e to the power of minus j 2 pi by 6 can be written as 2 into 3. So this can be written as minus j 2 pi by 2 into k by 3. That is w2 to the power of k by 3. So 2 plus w6 to the power of k can be written as w2 to the power of k by 3 into 1 plus w6 to the power of 2k will be w3 to the power of k. w6 to the power of 4k will be w3 to the power of 2k. Just 4 2 2s are 2 3s. Now x1 of k is this much. That means x1 of k by 3 is how much? In place of k we are replacing k by 3. So this will be 2 plus w2 to the power of k by 3. So 2 plus w2 to the power of k by 3 is x1 of k by 3 into 1 plus w3 to the power of k plus w3 to the power of 2k. So we have verified the result. So in this question, let x of z denote z transform of x of n. x1 of k represents the samples of x of z evaluated on unit circle at 10 equally spaced points, and z is given by e to the power of j 2 pi k by 10. So we have to determine 10-point IDFT, that is x1 of n from x1 of k. So we know x of z is summation n is equal to minus infinity to infinity x of n z to the power of minus n. Here 3, 3, 6, 7, 8, 9 samples have been given. 10 sample you can consider it as 0. So this can be changed to, the limits can be changed to 0 to 9 x of n z to the power of minus n. So from this you will get summation n is equal to 0 to 9 x of z to the power of n. When you substitute 0, 1, 2, 3 etc., you will get x of 0 is 2. So 2 z to the power of 0 plus 1 into z to the power of minus 1. You will substitute n is equal to 1. Substitute n is equal to 2. N is equal to 3. When you substitute, we know x of 3 is 0. Next substitute n is equal to 4. n is equal to 5 and you substitute x of 5 is 0 again. Next substitute n is equal to 6, 7 and 8. Last sample also we consider 0. So 9, when n is equal to 9, x of 9 is 0. So this is the Z transform of the given sequence. Now it is given that this x of z is sampled. 10 equally spaced points have been considered. By substituting z is equal to e to the power of j 2 pi k by 10. So when z is equal to e to the power of j 2 pi k by 10, we will get x of k that will be equal to summation n is equal to 0 to 9 x of n e to the power of minus j 2 pi n k by 10. So in place of z I have replaced it with e to the power of j 2 pi k by 10. So this is 10-point DFT of x of n. Now determine 10-point IDFT of x1 of k. Okay, instead of x of k I should write x1 of k, because in the question x1 of k is given. x1 of k represent the samples of x of z. So from x of z you got 10 samples, 10 equally spaced samples, by taking z is equal to e to the power of j 2 pi k by 10. So we got this, and this indicates 10-point DFT of x of n. So naturally, what is x1 of n then? x1 of n in the question it is IDFT of x1 of k, and IDFT of x1 of k from the previous expression, that is this expression, it is nothing but x of n. So IDFT of x1 of k is x1 of n is x of n. That is our original sequence 2 1 1 0 2 0 3 4 6 0. So this is the solution. Here number of samples were 9, and while sampling 10 samples had been taken. So input samples are 9. After Z transform 10 samples have been taken. So 10 is greater than 9. So we get the same expression. That means no aliasing, properly input sequence has been reconstructed back. Now consider this question. X of n is equal to 1 from 0, n ranging from 0 to 5. X of z is the Z transform of x of n, and this case it is sampled in such a way that z is equal to e to the power of j 2 pi k by 4. That means we are considering 4 samples. Originally 6 samples are there in the input signal x of n, but after x of z is found out, x of z is sampled. When x of z is sampled, only 4 samples have been considered here. So naturally aliasing will occur and original sequence cannot be retrieved back from the samples. So we know that aliasing is nothing but mixing of the signals. So first let us find the Z transform. We know x of z is equal to summation n is equal to minus infinity to infinity x of n z to the power of minus n. In this case it is n is equal to 0 to 5 and x of n is 1 in this case. So z to the power of minus n we will get. So this is equal to, you substitute n is equal to 0, 1, 2, 3, 4 and 5. Now this is the Z transform. But now x of z is sampled by taking z is equal to e to the power of j 2 pi k by 4 and k ranging, sorry, this should be k, so k ranging from 0 to 3. So if I substitute the z value in the normal formula, we will get x of k equal to summation n equal to 0 to 5. In place of z, I am writing e to the power of j 2 pi k by 4 to the power of minus n, so minus j 2 pi n k by 4. So because it is e to the power of minus j 2 pi n k by 4, that means 4-point DFT has been chosen. But the input length is 6. Therefore, there will be aliasing. And when IDFT of x of k is found, that means the input time domain sequence is found, we know aliasing will occur. So we will just expand this. So first substitute n is equal to 0, next n equal to 1, 2, 3, 4, and 5. Now this is 1 plus e to the power of minus j pi k by 2 plus e to the power of minus j pi k, e to the power of minus j, this will be 3 pi k by 2, e to the power of minus j 2 pi k, which is equal to 1, plus e to the power of minus j 5 pi k by 2. So here this is 1 and e to the power of minus j 2 pi k is 1, so 1 plus 1 you got 2, plus e to the power of minus j 5 pi k by 2 and e to the power of minus j pi k by 2 will be equal. E to the power of minus j pi k by 2. And now remaining terms, e to the power of minus j pi k, e to the power of minus j 3 pi k by 2. So here aliasing has occurred. You can see first term and the second last term have been mixed. Second term and last term have been mixed or added, and we have got 4 samples because here n is equal to 4 has been chosen. So from this, when you take the, so this is x of k. So let us assume y of n is IDFT of x of k. Then the IDFT will give me, this is 2. So I'll get 2 delta of n. this is e to the power of minus j pi k by 2 or e to the power of minus j 2 pi k by 4. So e to the power of minus j 2 pi by 4 is w4. So this is w4 to the power of k. So when I apply IDFT, I'll get 2 delta of n minus 1. And next, e to the power of minus j pi k is e to the power of minus j 4 pi k by 4, which is e to the power of minus j 2 pi by 4 into 2k. So IDFT is delta of n minus 2. Next, e to the power of minus j 3 pi k by 2 or e to the power of minus j 6 pi k by 4 is equal to e to the power of minus j 2 pi by 4 into 3k. So this will be delta of n minus 3. Or if you want me to write this as 2 plus 2, this will be w4 to the power of k. This will be w4 to the power of 2k, w4 to the power of 3k. So IDFTs are written in terms of impulse. Because delta of n minus n naught, the DFT is w4 to the power of n naught into k. Or IDFT of w4 to the power of n naught into k is delta of n minus n naught. That is IDFT of w4 to the power of n naught into k is delta of n minus n naught. So we have got, if you want to write it as a sequence, you can write it as 2 2 1 1. See, original sequence had 5 ones. Now because of taking only 4 samples per cycle, when you found out the IDFT or when you reconstructed back the original sequence, you can see original sequence is not equal to the actual input sequence. Because aliasing has occurred. So that's why you have to take care that when you take samples of the continuous signal, the number of samples taken should be greater than or equal to the number of samples present in the time domain sequence. Here in the time domain sequence 6 samples were present, but here x of z, when it is converted to x of k, or in other words when sampling of x of z takes place, only 4 samples were taken and 4 is less than 6, so that's why aliasing has occurred. Next, an analog signal is sampled at 10 kilohertz. So DFT of 512 samples is computed. Determine the frequency spacing between spectral samples of DFT. So here sampled at 10 kilohertz, so Fs is equal to 10 kilohertz. Samples 512 samples, so N is equal to 512. So you have to determine the frequency spacing. So delta F is given by Fs by N, and delta omega is nothing but 2 pi into delta F by Fs, which is equal to 2 pi by N. So Fs is 10 kilohertz, N is 512. So this when you divide, it is 1.95 hertz, or you convert into radius, it will be 2 radians, it will be 2 pi by 512. Next, endpoint DFT of endpoint sequence x of n is given. X of n is given, endpoint DFT is given as x of k. You have to determine 2 endpoint DFT of 2 endpoint sequence. You can see y of n and x of n are same. Only thing is x of k is endpoint DFT, and you have to determine now 2 endpoint DFT of the sequence. So x of k is endpoint DFT, so n is equal to 0 to n minus 1, x of n wn to the power of nk. X of k is endpoint DFT of x of n. Now you have been asked to find out 2 endpoint DFT of y of n, but you can see y of n and x of n are same. So 2 endpoint DFT, let us take it as x of k. It is equal to summation n is equal to 0 to 2n minus 1. We'll take y of n w2n to the power of nk. So this we will split into 2, summation 0 to n minus 1 and summation n to 2n minus 1, y of n w2n to the power of nk. So like the one which we had done previous problem, like same like that, we have here you have to do summation 0 to n minus 1 y of n w 2n to the power of nk plus summation. Here from the limits we will subtract n, so inside wherever n is there we have to add n. So n is equal to 0 to n minus 1 y n plus n w 2n to the power of n plus n into k. So this is summation 0 to n minus 1 y of n w 2n to the power of nk plus summation n is equal to 0 to n minus 1. Y of n plus n will be equal to y of n, because y of n is 2 endpoint sequence and it is equal to x of n. So it is w, when I expand this will be w 2n to the power of nk and w 2n to the power of capital NK. So we will take out summation n is equal to 0 to n minus 1 y of n. Now w 2n to the power of nk, this I'll take common, so I'll get 1 plus w 2n to the power of nk. So here w 2n to the power of nk can be written as this one, it can be written as wn to the power of n k by 2. Similarly here this n cancels and this term is w2 to the power of k. So we get summation n is equal to 0 to n minus 1 y of n wn to the power of n k by 2 is equivalent to x of k by 2. Why? Because y of n and x of n are equal and summation n is equal to 0 to n minus 1, that is endpoint DFT. The wn to the power of n k by 2, it is endpoint DFT only by comparing with the first expression, but instead of k, here k by 2 is there. So instead of x of k, we will get x of k by 2 and into 1 plus w2 to the power of k. Now what is w2 to the power of k? it is e to the power of minus j 2 pi by 2 into k, or e to the power of minus j pi k, which is equal to e to the power of minus j pi is minus 1 to the power of k. So when k is even, this w2 to the power of k will be plus 1, and when k is odd, this will be minus 1. So k even, then y of k will be equal to x of k by 2, 1 plus 1, 2 you will get. And when k is odd, y of k will be 0, because 1 minus 1 you are going to get. Now 2x of k by 2, that is 2 into x of k is given here. X of k by 2 will be obtained wherever k is there, you substitute k by 2. So this will give us square root of n e to the power of minus j pi by 4 e to the power of j pi by n. Instead of k square, we will write k by 2 whole square. Next, if x of k is the DFT of x of n, show the DFT of x of n is nx of minus n. First, we have to find out DFT of x of n. DFT of x of n is x of k, so DFT of x of k we have to find out. And what is DFT of x of k? It is equal to summation k equal to 0 to n minus 1 x of k wn to the power of nk, where in this formula of DFT, instead of n, k is written, and instead of k, n is written. Now this I can convert it into IDFT formula by writing summation k equal to 0 to n minus 1 x of k wn to the power of minus k minus n. So minus of minus, so it will be give us plus nk. And what is the formula of IDFT? X of n is equal to 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of n minus nk. So nx of n is equal to summation k equal to 0 to n minus 1 x of k wn to the power of minus nk. Now when I compare with the formula, these two will compare. Summation k is equal to 0 to n minus 1 x of k wn to the power of minus nk, here wn to the power of minus k into minus n. That means instead of n here minus n is there. So this I can write it as nx of minus n. See, if minus nk is there, this is nx of n. But in this formula, wn to the power of minus k into minus n is there. So instead of n, we are writing minus n. That is the first part. Now second part is we have to find DFT of x of n. Now DFT of x of n, this much we have already found out. It is DFT of n x of minus n, and we can take out now what is DFT of x of minus n? Formula: n is equal to 0 to n minus 1 x of minus n w n to the power of nk. So this will give me n. Now here minus n is there, so if I take minus n is equal to m, then in that case minus n is equal to m, or m is equal to minus n. Then the limits will change to m is equal to 0 to minus of n minus 1 x of m w n to the power of minus mk. Now because it is periodic, 0 to minus of n minus 1, this I can change to 0 to n minus 1, because you know the points 0 to n minus 1 or minus of n minus 1 to 0, it is repeating, the points are repeating themselves. So every time the n points repeat. So we have n summation m is equal to 0 to n minus 1 x of m w n to the power of minus mk. So here the formula of IDFT, if I check, instead of k m is there, and instead of n k is here. So you can see m is equal to 0 to n minus 1, here x of k, here x of m, w n to the power of minus mk, here minus nk. So from this I can write this n is already there into n x of n is IDFT of x of k. So here it will be IDFT of x of m, that is n square into IDFT of x of m. Got it? So n is anyway there, so n into, now this formula and this formula are equivalent, and that means this formula is equal to n into x of n, where x of n is IDFT of x of k. So that's why, because these two formulas are equivalent, from this formula I'll get IDFT of x of m. So DFT of x of n is equal to n square into IDFT of x of m. Next, compute the endpoint DFT of the sequence x of n is equal to an. So we have got x of k equal to summation n is equal to 0 to n minus 1 x of n, here x a n, w n to the power of nk. Because a is a constant, I'll take it out of the summation. 0 to n minus 1 n w n to the power of nk. For this summation formula is not there. So let us take summation n is equal to 0 to n minus 1 b to the power of n. We'll get 1 minus b to the power of upper limit plus 1 by 1 minus b. Now apply or differentiate both sides with respect to b. So here we will get summation n is equal to 0 to n minus 1. Differentiate with respect to b, I will get n b to the power of n minus 1. And here I will have to apply u by v rule. So v into differentiation of u minus u into differentiation of v by v square. And b to the power of n minus 1, I can write it as b to the power of n by b, so that b, which is dividing this side, if it goes, it multiplies. So we will get summation n is equal to 0 to n minus 1 n into b is equal to b into, now this I will expand, I will get minus n b to the power of n minus 1. This will be plus n into b to the power of n, minus into minus plus, so plus 1 minus b to the power of n by 1 minus b whole square. Now here whatever I got, summation n is equal to 0 to n minus 1 nb, and here summation n wn to the power of nk. This is b to the power of n. B to the power of n minus 1 is written as b to the power of n by b. That b we have brought it to the other side. So from these two expressions we can replace b with w n to the power of k. So summation nk is equal to wn to the power of k minus n wn to the power of k into n minus 1 kn we'll get here one minus wn to the power of k whole square. So wn to the power of k, wn to the power of kn. Now this is equal to minus n, wn to the power of kn is 1, so we'll get wn to the power of minus k, wn to the power of kn is 1, so plus n plus 1, and wn to the power of kn is 1 minus 1, so cancel by 1 minus wn to the power of k whole square. So this is equal to, I take n common and multiply with wn to the power of k, I will get wn to the power of k minus 1 by, because this whole square is there, I can change this to wn to the power of k minus 1 whole square. So this is n by wn to the power of k minus 1. So x of k we have to multiply a. So x of k is equal to a into n by wn to the power of k minus 1. Now here we have to once again check whether the denominator becomes 0 for any condition of k. So we know that for k equal to 0, wn to the power of k will become 1, so that denominator becomes 0. So this result is for k not equal to 0. But if k equal to 0, then what we have to do? We have to substitute this condition in our original formula. That is here, when k equal to 0, if I substitute, x of k will be summation n is equal to 0 to n minus 1 an. So x of k will be summation 0 to n minus 1 an. So a is constant. Summation of n, we will get n minus 1 into n by 2. So as a whole, x of k is an by wn to the power of k minus 1, k is not equal to 0, and it is equal to an into n minus 1 by 2 when k equal to 0. Next, find endpoint DFT of x of n. X of n is given. So cos square theta is there. Cos square theta is cos 2 theta plus 1 by 2. So x of n can be written as 4 plus half into 1 plus cos 2 theta, that is 4 pi n by n. So here 4 plus half will give me 9 by 2 plus half cos theta is e to the power of j theta plus e to the power of minus j theta by 2. Or if I convert this into twiddle factors, so at 1 by 9, 9 by 2 plus 1 by 2 into 1 by 2 will give me 1 by 4. E to the power of j 4 pi n by n is e to the power of j 2 pi by n into 2n. So this will be wn to the power of 2n plus wn to the power of minus 2n. E to the power of minus j 2 pi by n into 2n. So now apply the formula to find out the DFT. Summation n is equal to 0 to n minus 1. You have n by 2 plus 1 by 4 wn to the power of 2n plus 1 by 4 wn to the power of minus 2n wn to the power of nk. So summation n is equal to 0 to n minus 1. We will multiply and then split the summations. So we'll have 9 by 2 wn to the power of nk plus 1 by 4 summation n is equal to 0 to n minus 1 wn to the power of, I'll take n common, so k plus 2 I'll get 1 by 4 summation n equal to 0 to n minus 1 wn to the power of n into k minus 2. For this next term I have taken n common, so k minus 2 I'll get. Now find out the summation. So 9 by 2 into, this is a to the power of n, summation a to the power of n. So 1 minus wn to the power of k upper limit plus 1 by 1 minus wn to the power of k plus 1 by 4 into 1 minus wn to the power of k plus 2 into upper limit plus 1 by 1 minus wn to the power of k plus 2 plus 1 by 4 1 minus wn to the power of k minus 2 into upper limit plus 1 by 1 minus wn to the power of k minus 2. So all these terms are equal to 1. This is equal to 1, this is equal to 1, this is equal to 1. So numerator of all the summations are zeros. Now we have to check for what condition of, or for what value of k the denominator might become 0. So each one will have to answers. Here when k equal to 0, wn to the power of k will be 1 and the denominator will become 0. So for k not equal to 0, the solution of this summation is 0. 0 by 1 minus wn to the power of k is 0. But when k equal to 0, denominator will also become 0. It will be 0 by 0 form, which we cannot take. So we have to substitute k equal to 0 in the summation. So 9 by 2 into summation of n is equal to 0 to n minus 1 of 1 we will get, which is 9n by 2. And now next summation, if k equal to minus 2, then denominator will become 0. So when k is not equal to minus 2, then denominator is not 0, only the numerator is 0. So this ratio will become 0. But when k equal to minus 2, then you will get 0 by 0 or indeterminate form. That's why we'll substitute k equal to minus 2 in the original summation. So we will get 1 by 4 summation n is equal to 0 to n minus 1 of 1, and the answer is n by 4, 1 by 4 into n or n by 4. And for this one, k equal to 2, the denominator will become 0. So for k not equal to 2, the solution of this summation is 0, because numerator is anyway equal to 0. And when k is equal to 2, even the denominator will become 0 in addition to the numerator, so that we cannot consider. So substitute the condition k equal to 2 in the summation. So we'll get 1 by 4 summation n is equal to 0 to n minus 1 of 1. That is 1 by 4 into n or n by 4. So together when we take x of k equal to 9n by 2 when k equal to 0, that means delta k, plus n by 4 when k equal to minus 2, so delta of k plus 2, plus n by 4 delta of this is occurring at k equal to 2, so delta of k minus 2. So this is the answer. So we have solved the problems based on DFT and IDFT formulae. So in the next video lecture, we are going to go through the properties of the DFT. Thank you and have a good day.